Hi, I'm Professor Goins. In this video, I'm going to take a look at the differentiation rule called the product rule. What I'm going to do is I'm going to start with the statement of the rule. I'm going to work through a variety of examples, and then for those that want to see where this comes from, because this is a fairly strange looking rule, I'll prove this at the very end of the video. But again, I'll let you know when I'm about to do that. But if you only want to see how it works through examples, then we'll work through A through D. If you want to see again where this comes from, feel free to watch the entire video where I'll walk through the proof of it. Okay, so the product rule has to do with differentiating a function that's built with multiplication. So what I have is two different factors written as f of x and g of x. And again, I have to recognize the structure of that function is an expression multiplied by an expression. And the idea is I can use the product rule if I know the derivative of each of those two factors. Now, if you're watching this video, chances are you're in the beginning of a Calc 1 class and you may or may not know all of these different derivatives. Some of these you may want to just bear with me and just pretend like you know what it is, like you know what the derivative of tangent is. The main idea is we're going to walk through how the product rule works. But I'm going to look at the following functions. A polynomial term in e to the x, so an exponential, but is specific, the natural base. A tangent function, a logarithm, a cube root, sine function, and then another polynomial term. So if you don't know some of those, it's no big deal. You can just kind of follow along and just, again, see how the formula works. Okay, so solution. Let's see, let's go right here. Part A, the derivative of y, so in other words, dy dx, is equal to, well, if I look at this expression here, I've got x squared multiplied by e to the x. That follows this form. This would be your x squared. This would be your e to the x. And what the product rule says is I take the derivative of the first factor being x squared. Therefore, this gives me a 2x multiplied by the second factor, which is e to the x. Plus, then after the first term, I leave the first factor alone, so the original factor would be x squared, and then multiply by the derivative of g, so the derivative of the second factor being e to the x, and of course its derivative is e to the x. This then is the result of differentiating x squared e to the x. Part B. All right, let's look at the structure. I've got a product of a tangent and a logarithm. Each of these we know the derivatives of, and like I said, you may not, depending on where you are in your Calc 1 course. I'll tell you what they are in case you're not sure, but the first thing we do is I take the derivative of the first factor, and the derivative of the tangent is the square of the secant, multiplied by the second factor, which is the logarithm, plus the first factor, f of x, so in other words, the first factor, tangent, and then I'll multiply by g prime, which is the derivative of the second factor, which is the natural log, and the derivative of the natural log is the reciprocal of the input. Okay? This right here then would be the result of taking the derivative of tangent times natural log. Part C. Cube root, what we do with that as a reminder is we write this as x to the 1/3. So I'll write a radical with an exponent that would be x to the 1/3 multiplied by sine of x. You don't have to, but it is a good reminder to walk through the power rule. Okay. All right. So the derivative of this product right here, again, f prime, derivative of the first factor, which would be 1/3 x to the negative 2/3 multiplied by the sine function, so multiplied by the second factor, plus the first factor, which is x to the 1/3, multiplied by the derivative of the second factor, the derivative of the sine function being the cosine function. We could then clean this up. So this would be, depending on your instructor, this could be okay as a final answer for, homework or an exam or a quiz. It's not a textbook answer. Textbook answers will always simplify this so that there's not a negative exponent, and chances are it'll rewrite this as a radical, this one as well, a radical in the denominator. But for now, we'll just leave it as is. Finally, part D. All right, let's look at the structure of this. What's this built of? I've got 5 multiplied by x to the 4th. Now, what's different about this one, even though there is a product between two factors, this is the first factor is a constant. So you can do this using the product rule, which let's go ahead and do it. But then we'll see why it's, I don't want to say a waste of time, I'll just say less efficient. dy dx. Okay, so this would be the derivative of the first factor. The derivative of a constant is 0. This would give you 0 times x to the 4th. Plus the first factor, which is 5, multiplied by the derivative of the second factor. The derivative of x to the 4th being 4x cubed. This then reduces to 20x to the 3rd. Notice this first term is 0. And if I take that part away, look what this is. This is the constant multiple rule. Therefore, if I have a function built as a product, I'm not always going to use the product rule. I'll use the product rule in the case where f of x and g of x, neither of those are constants. If one of those is a constant, then you can just use the constant multiple rule. That is to say, though, if you did the product rule, you're not going to get a wrong answer, assuming you do all the derivatives correctly. You're not going to get an incorrect answer. It's just less efficient. All right, this is how this is the statement of the product rule. This is how you work through a variety of examples. If anybody wants to see where this rule comes from, let's take a look at the proof of that. It's pretty straightforward. All I have to use is the definition of a derivative using limit of a difference quotient. But there is a little trick there, and that little trick is why we get this. Okay, let's take a look at that. Proof. So for this statement right here, the derivative of the product is given by that. Here's the proof of it. The derivative of any function is the limit of the difference quotient. If f of x times g of x is my function, then the difference quotient would be that function evaluated at x plus h minus the original function divided by h. Now, here's the trick. I'm going to add and subtract an expression in between those two. In particular, I'm going to add and subtract something that equals 0, so I'm not changing the value of this expression, but I'm going to specifically choose it so that I end up getting this result. Okay. Here's what I'm going to add and subtract. I'll do this in a different color. I'm going to subtract, let's see, I'm going to do f of x, g of x plus h. I'm going to add the same thing. Add f of x, g of x plus h, and then I still have my minus f of x, g of x on the end. And that whole thing, of course, is divided by h. All right. Everything in red there equals 0 because it's the same exact term, one with a plus, one with a minus. Now what I'm going to do is I'm going to group together the first two terms. So I'm going to group these two together and I'm going to group these two together. And I'm going to do it while also factoring. Look at these first two terms. What do they have in common? Both of these have a g of x plus h. Therefore, I can factor g of x plus h out of the first two terms. What do these two terms have in common? They both have an f of x. I can factor f of x out of the second term. All right, let's rewrite this limit statement while factoring those out. This gives me the limit as h goes to 0. And again, I factored out g of x plus h. The way I'm going to factor it out is traditionally we take that and we put it in the front when we factor something out, but multiplication's commutative, so I'm going to factor it out on the right-hand side. This gives me f of x plus h minus f of x multiplied by g of x plus h. Another thing I'm going to do, this isn't necessary, but I'm going to separate the fractions. So I'll take these two terms over h and then plus those two terms over h. All right, plus. Now I'm going to factor f of x. I'm going to factor that out on the left. That gives me f of x multiplied by g of x plus h minus g of x all over h. All right. Take a look at that expression and take a look at the expression that we're trying to prove up in red. Notice something. When I take the limit as h goes to 0, this first factor, remember, limit of a product would be product of the limits, and the limit as h goes to 0 of what I just circled is the derivative of f. This would be f prime of x. When I take the derivative of this factor here, if g is differentiable, then g is also continuous. Therefore, I can interchange the limit and the function, taking the limit as h goes to 0 of x plus h, giving me g of x. Looking good so far. Then I say plus. Well, this first factor here is independent of h, so it's just that constant with respect to h. Therefore, the limit would be f of x. Then look at this part right here. That's the difference quotient for g. Therefore, when I take the limit as h goes to 0 of the difference quotient of g, we get the derivative of g, thereby proving the product rule. And again, notice when I added and subtracted those two terms in the middle and then separated that, so separating from here, this plus is the plus up in the product rule. That's why I've got two terms. And then notice that here I've got a difference quotient times a function. Here I've got a function times a difference quotient. We take the limit of those difference quotients, that's where the derivatives comes from. So again, that's where the product rule comes from.